Alright guys, so part C is telling us to integrate 1 over v times v plus 3 squared dv. You should be able to recognize this as an ideal candidate for partial fractions, because we see that the denominator is nicely factored and set up for it. So we can set up the partial fraction, the integral of a over v plus b over v plus 3 plus c over v plus 3 squared. Let me just explain this over here. So if you have a fraction like this, so in other words, it's of the form ax plus b square to the power of k, its partial fraction would be turned into this a1 over ax plus b. So you go up to k, so plus b a2 over ax plus b 2, and then you keep going up to k, a k over ax plus b k. So that's what we did exactly here. We have v plus 3 squared, so we did v plus 3, and then the next one was we're going up to k. A k in our case is 2, so we're going up to 2. So that's how our partial fraction is split up. Let's carry on here. So to do partial fractions, what you do is you're going to set up equation by basically multiplying, cross-multiplying here. So if I were to multiply all of this out, I would get 1 is equal to, so a v plus 3 squared, a times v plus 3 squared, the v's will cancel out, so we'll get a v plus 3 squared time plus b v times v plus 3 and plus c v. That's what you get for cross multiplying all that out. So now what we do is we pick values of v that cancel some certain things out, so that we can isolate for either a, b, or c. So for example, if we set v equal to 0, we would know that this here would go to 9, would become 9. This whole term would go to 0, this whole term will go to 0, so we'd get 1 is equal to 9a, and we realize that a is equal to 1 over 9. Say we picked v is equal to -3, because we pick it so that this term can go to 0. This term also goes to 0, so we get -3c is equal to 1. 1 is equal to -3c, and we know that c is equal to -1/3. And if we picked v is equal to -2, in that case you would get 1 over 9 times 1 squared plus b -2 times 1 plus 1/3, minus 1/3 times minus is positive, so 2, and then we would get that b is equal to -1 by 9. Alright, so oops. Now we can we have values for a, b, and c in our newly formed partial fraction, so we can rewrite this integral as 1 by 9 over v minus 1 by 9 over v plus 3 minus 1 by 3 v plus 3 squared, and all that's dv. Now we have pretty simple integrals to do. We know that the integral of something over v is ln, so we would bring this 1 over 9 in front of the integral, so we would get 1 over 9 ln v. And this one here, you have to you would get basically ln v plus 3 to the 1 over 9. Same thing as the first way we derive it. And the last one would be 1 over 3 1 over v plus 3 plus c. I've shown in previous videos how to derive, integrate something over v plus 3 squared. And don't forget the constant of integration. So now we can simplify this further by bringing this to an exponent in front of the ln. So we get ln v 1 by 9 minus ln v plus 3. These are absolute symbols. 1 over 9 plus 1 over 3 v plus 3 plus our constant. And further simplifying, we know that by logarithmic rules these two are subtracted, so they can be put in a quotient at root 9, ninth root of absolute value of v over absolute value of v plus 3, and plus the rest. So you see, doing integrals is all about figuring out what method you're going to use by just looking at it and analyze, taking like a minute to just figure out which method is the best to do it. We got one more to do in this question, so let's get to it. Alright guys, question D is asking us to take the integral of e to the power of root 3x plus 1 dx. You look at this integral and you see that it looks pretty simple. It's just e to the power of some variable under a square root. But no, it's not that simple. There's no really easy answer to this. You actually have to use substitution. It's the perfect candidate for it. And it's not just going to be an easy substitution. We're going to have to do a little bit of work after, but you'll see. You'll get it. So let's say we call the variable t square root of 3x plus 1. When we make that substitution, we would get e to the power of t dx. These variables are different, right? We got t and x, so we need to get rid of this dx somehow. So let's say we take the derivative of t, and then we would take the derivative of that side as well. So the derivative of the right side is 3x plus 1. So this can be rewritten as 3x plus 1 to the half. So you bring the half to the front, 3x plus 1, multiplied by the derivative of the inside times 3. So dt is equal to 1/2, well, 3 over 2, 3x plus 1. You have to subtract 1 from the numerator, the exponent, right? So this becomes negative 1/2 is equal to 3 over 2 root 3x plus 1. Right, because you bring this into the denominator, the exponent becomes positive, and you have this, basically have a square root. So, and don't forget the dx here because you derived both sides here. So now the only simple thing to do is to plug in for dx. Just note that we had declared that this was equal to t, so our actual derivative here is 3 over 2 t dx. So knowing that dt is equal to 3 over 2 t dx, we can make the substitution, isolate for dx. Dx is equal to 2t dt over 3. So we get the integral of e to the power of t, 2t dt over 3. And we pull out the 2 over 3, t. Right, so you should be able to recognize that now we have, whenever you have an integral of some variable x multiplied by e to the power of x, this is integration by parts off right away. So the integration by parts is integral of u times v. So this is the first term, second term multiplied, like e and t, e to the power of t times t is integral of uv goes, it's uv, and it's integral of u dv minus uv is equal to uv minus integral of v du. So our u and whatever's left over is dv, right? So let's say we call u is equal to t, and whatever's left over is automatically our dv, which is et dt. So dv is whatever's left over. So you always make u the easier term, and whatever's left over is your dv. So right, you always want this expression here to be matched with the dv, right? So it makes the integral really easy. So now you take the derivative of the first side, so that's 1, and you dt, and then you take the integral of this side. The integral of e to the power of t dt is just e to the power of t, and you apply this this rule here. So the integral of e t dt is equal to all this. So u times v, so t e to t, minus the integral of v, so e to the power of t, du, so dt. And that's a really easy integral, so it's t e to the power of t minus et plus c, and we have to multiply everything by the 2/3 that we had in the beginning. So our integral will be 2/3 t e t minus 2/3 e t. I mean, you could write 2/3 c, but it's still just a constant whether you multiply it in or not. So you can just leave it as c because it's still always a constant. And then we just sub back in whatever we established was t, which is a messy expression. 3x plus 1 e to the root 3x plus 1 minus 2/3 e to the root 2x plus 1. And there you go, folks. That's the answer to this question. Alright guys, question 3 says to find the average value of the function f of theta is equal to tan cubed 3 theta on the interval 0 to pi by 12. The actual just finding the average is, setting up the equation to find the average is the really easy part. It's actually solving the integral that's the tough part. So the formula for the average value of a function is 1 over b minus a, where the b and a are your bounds. A to b, integral, not double integral, we're not in Cal 3 yet, f of x dx. Alright, so let's go ahead and work here. We plug in our bounds. 1 over pi minus 12 minus 0 is pi minus 12. Integral of 0 to pi by 12. And our function is tan cubed 3 theta. Alright, that's setting up was the easy part. It's not solving the integral. That's the really hard part, because this is not a really easy integral, but there's a trick, and it's when you have when you're taking the integral of a trigonomic term to raise to some power, even if it's like to the power of 7, 6, 5, whatever, you just separate it into smaller powers of tan. So what I mean here is that if I rewrite this, and this constant here in the front of the integral it becomes 12 by pi. Integral 0 to pi by 12. Now let me go ahead and split this up into tan squared 3 theta, tan 3 theta. The reason we do this is that if we make a substitution, we can greatly simplify this this equation. There's a d theta there which I didn't put before, but so let's go continue on. Let's replace this with the trig identity we're using here is tan squared 3 theta is equal to 1 minus secant squared 3 theta. So if I go ahead and plug that in, 12 by pi, 1 minus secant squared 3 theta tan 3 theta d theta. So now, like, if I go and make my substitution, it's equal to just secant 3 theta. Derivative would be, and I'm assuming you know how to do basic derivatives, or else you wouldn't be doing calculus 2. So that's that. So our derivative would be 3 tan 3 theta secant 3 theta and d theta. So you see that if I replace, if I plug in my u that I just declared was secant 3 theta, I'll get 1 minus u squared. And now we're left with this tan 3 theta d theta. We need to get rid of that, right? So we can all make everything in terms of u. So I do have it here. It's right here, tan 3 theta d theta. So if I isolate it for, and we declared that this was u from the line above, so I have du over 3u is equal to tan 3 theta d theta. And that's exactly what I can plug in here. So du over 3u. So now if I bring this 3 out to the front to join d12 by pi, 12 by 3 pi, integral 0 to pi by 12, 1 minus u squared over u du, and I can distribute this integral to each term, so I get the integral of, and split, if I split this this numerator and denominator, term-wise division, I get 1 over u minus, so u squared over u is just u, and all of that times du. From 0 to pi by 12, 0 to pi by 12. Okay, I'm not going to continue solving this because it's a really trivial integral. This will be just be ln of u, and this would be u squared over 2. And then you plug in your bounds. Don't forget to substitute back in what we originally declared was our u. So secant squared 3 theta's got to go back in there before you submit your final answer. I just want to note that at the original start of the problem, we could have chose that our u was going to be tan 3 theta. Instead, we could have chose that, and then our du would have been 3 secant squared 3 theta. It would have been a result of the same answer. I encourage you to double check that if you want. So let's move on to the next question. Alright guys, question 4 asks you to find the value of the integral 0 to 1 x cubed ln x, or show it diverges. We're just going to do both because that's what it's asking. We're going to find if it converges or diverges, and if it converges, what does it converge to. So the important thing here, guys, to note is that this is an improper integral. And you'll know that because if you take one of these bounds, so 0 to 1 x cubed ln x dx, if you take one of these, like a bound, one of the bounds 0, you plug it into either, like if you plug it into x cubed, the whole term goes to 0. If you plug it into ln x, ln of 0 is not defined, so that makes the integral, it's an improper integral, it doesn't make sense. Whereas all the other integrals we've done, you can plug in the bounds and it makes sense, there's no problem. You get an improper integral when one of your bounds plugged in leads to something that doesn't exist or is not defined. So the way to transform a proper integral, and sometimes improper integrals come with an infinity sign in them, then you know it's an improper integral. But to transform an improper integral of this kind, you would rewrite it as the limit as t approaches 0 of t to 1 x cubed ln x dx. So what I did here was I replaced our bound that's causing an issue with a t, put it to the other bound, and then we're taking the limit as t goes to 0. This doesn't mean that we still don't have to solve this integral. We have to actually determine what that integral is and then plug in our values. So we have a term multiplied by a term, so this is a perfect candidate for integration by parts. Alright, so let's do it. the integral of uv is uv minus integral of v du. So we'll pick our u's and our dv's. So our u will be our ln x, nice and simple term. The derivative is really simple, 1 over x dx. And then whatever's left over is your dv, so x cubed dx. And the integral of that is 1 over 4 x4. All right. So now we can set up this integral, so the integration by parts. So is equal to, so u times v ln x, so times 1 by 4 x4, and the integral should be this one here. The integral v du should be the really easy. So if it's so complicated, you're doing something wrong. So v du, so v is 1 quarter x4 times 1 over x dx. Right, so this would cancel, this would become 3, this would cancel out, so we get the integral, the integral is, and I forgot my integral sign here, ln x, 1 by 4 x4 minus the integral of x cubed over 4 dx. And these are from 0 to t. Here, right here, it's from 0 to t. So, no, that's wrong, it's from 1 t to 1. Perfect. Now all that's left to do is calculate the integral and then take the limit of it after. So our integral is, so I'll rewrite everything. Limit as t approaches 0 of 1 by 4 x4 ln x. So this integral, add 1 to the exponent, divide by the exponent, so x4 over 16, evaluated from t to 1, and this ends up being the limit as t approaches 0 of 0 minus 1 over 16, so I'm putting things like that, minus 1 by 4 t for ln t minus t for over 16. Alright, so we can start to taking the limit as t goes to 0. What happens when t goes to 0 when you plug it into the first term? So ln of 0, this and ln of 0 will go to negative infinity. This one will go to 0, and this one will go to 0 as well. So we'll have a function that looks like this: negative 1 by 16 limit as t approaches 0, 1 by 4 t for ln t. This term, we still got to figure out what's going on here because we have a 0 and a negative infinity here. That's the way these terms approach. So what we're going to do here is we're going to apply L'Hopital's rule, because we can't really say that this is going to negative infinity, this first term, just because, or is it going to 0? We can't really say it, so we can rewrite this as negative 1 by 16 limit as t approaches 0 of ln t over 4 t negative 4. So now if we apply L'Hopital's rule, this will end up being negative 1 over 16 minus limit t over 0, 1 by t, derive the numerator, derive the denominator, negative 16 t negative 5. Can we conclude anything from this yet? No, because we have 1 over 0 on the numerator and 0 on the denominator. So we can apply it one more time, taking the derivative of the numerator and denominator. 16, limit as t approaches 0. There's a minus sign here. Minus. So taking the derivative, we get 1 over negative 16 t negative 4. And now we can work with it. So we can rewrite this as negative 1 by 16. Bring the t to the negative 4 to the top, because if you don't do that, you can't really evaluate this limit yet. You get t4 over 16. And you can conclude that this is going to 0. So you get negative 1 by 16 converges to this. So in recap, take your integral, realize that it's an improper integral because if you plug in your 0, you get an undefined ln x over here, which is causing a problem. So you replace your problematic bound with a variable t, go to 1, realize that this is integration by parts. So we apply the integration by parts, and we rewrite everything with our new limit, with the limit that we decided to take, and we just use L'Hopital's rule a couple times to get it in a form that is easily manipulated by plugging in our t value for 0, and we get an answer. I mean, all these problems are kind of a lot of work, but practice. Alright guys, question 5 is asking us to determine the total area of the region bounded by the following: y equals x cubed, y equals x squared, and y equals x equals 3. So what we'll do is we'll draw out, plot each function onto a graph. So we know that x cubed looks something like this. It's quadratic. X squared, sorry. X cubed will start off slow, but then it'll rise really fast. Alright, so and then we got x3, we'll say that 3 is here. x3, go like this. So the region's bounded by these 3 graphs. So here is a bounded region, right here. This is bounded between the graphs, and here as well. It's enclosed. That's what they mean. Enclosed by. Where is this enclosed by the graph? This is not a valid area because it's the x-axis. That's one of the bounds, which is not correct. So basically, we got to find the area of here and the area of here. So we do an integration. So we got to find out this point here because we're gonna have to do 2 integrals. One integral for this, one integral for this point here. So we need to know where our bounds are for each integral. So this point of intersection, I mean, the intersection of x cubed and x squared is 1. I mean, I can show it, but it's trivial stuff. You set them equal to each other. You go a little bigger. Divide both sides by x squared. You get x is equal to 1. Plug back x equals 1 into either function. So y is equal to 1. So our intersection point is x equals 1. So our first integral will be the integral from 0 to 1. And what functions are bounded here? So we got x cubed on this. This one is x cubed. This one is x squared. So x squared minus x cubed, because x squared is on top. Dx. And our second function is going to be from 1 to the outer bound, which is 3. And the top function is x cubed, and the bottom function is x squared. And that's it. We set it up. Our integral is really easy. So we get x cubed over 3 minus x4 over 4, evaluated from 0 to 1, plus x4 over 4 minus x cubed over 3, evaluate from 1 to 3. And doing so, we get 137 by 12 when we evaluate that. So it's a pretty easy problem. I mean, it's even fun to do, but yeah, math is fun. See you in the next problem. Alright guys, so that concludes part 2 of the exam. Just switch over to part 3 at the end of this video, so we'll continue the questions. Don't forget to like this video and subscribe to me so you have up to date on all the courses I offer. So I'll see you in the next part.